To have a visitor from University of Maryland. Abhinav Gupta is a finishing graduate student working with Larry Davis at Maryland and also our very own Jumbo Shi at UPenn. And he is entered the large prominence with a very, very insightful couple of works last year on going beyond nouns, and now I see that even verbs are not good enough. So I'm very interested to see what this is all about. So
thank you. So I'll be talking about beyond nouns and verbs, and this is a kind of recent work, as Alicia said. I did it during the last 1 year, and so I'll start with some basics, and so that if someone doesn't know about the problem, they can know the problem, and then I'll go on and talk about my work. Okay. So please excuse me for my voice. I got a really bad cold. Okay. So one of the long-term goals of the AI community has been to design intelligent machines and robots that can interact with human and help us in our daily activities, like help our children cross the road, help serve the food to the sick, and so on. Now let us consider one example interaction scenario where a human is trying to interact with a robot. Let us suppose the human asks the robot to hand him the cup. Now the robot can look up in its online dictionary and understand a cup is a utensil. It can maybe even understand from its dictionary that a cup is something similar to a mug and glass, and so on. However, such definition of the word cup will not really help the robot to localize the cup on the table. What it actually needs is a visual representation of the word cup. This visual representation can either be a histogram of intensity values, shape model, or something similar. And once it has this visual representation of the word cup, it can localize the cup on the table. So this problem of associating words in the language with the visual representation is called the visual grounding problem. As you can see from this example interaction scenario, the grounding of both nouns and verbs is important for designing these intelligent machines. So traditionally, people in computer vision have used large image data sets with some associated text or caption and use them to learn the appearance models of the words. So in such an approach, you first solve the correspondence problem, that is, you associate regions with the words, and then you learn the appearance model of the words. And once you have a new test image, you uniformly sample the windows in the test image and classify each window as either belonging to one of the object categories or the background. However, except for few classes like faces, such an approach has a very low recognition rate. One of the reasons for the low recognition rate is the correspondence ambiguity in learning itself. Now traditionally, computer vision people have used co-occurrence of words and visual features to solve the correspondence problem. So in this case, since visual features in the purple region and the word bear co-occur throughout the three images, it can be easily said that the purple region should be the bear, and so on. However, co-occurrences have its own problem. Most of the objects in the world occur in groups. For example, whenever you will see a car, you'll always see a road. So in such cases, it would be hard to argue whether the green region is the car and the pink region is the road, or the green region is the road and the pink region is the car. One of the other reasons for low recognition rate is the ambiguity in inference itself. So if you remember, we were sampling windows like these and trying to classify each of the window as belonging to one of the object categories. However, as you can see, this is a hard problem. But when you put these windows in the context of the whole image, you can easily say that this window is a road, this window is a car, and this window is a pedestrian. So one of the interesting questions is, what extra information do we extract from images that helps us in recognition? Now people have used geometrical information, that is, by extracting ground plane can help in recognition of cars, pedestrians, and so on. Global information, that is based on what kind of scene you are looking at, you know what kind of objects to expect. And semantic information, that is, based on what kind of objects you have found till now, you know what kind of other objects to expect. For example, in this case, the hypothesis that this region is a tennis ball is equally likely to the hypothesis that this region is a lemon, just based on appearances. However, since you have already detected a tennis racket, you can say that the first hypothesis, that this is a tennis ball, is more likely. Now from the first problem, it is clear that noun annotations are insufficient for solving the correspondence problem. That is, you need a much richer description of these images to constrain the learning problem. So so basically, instead of using the image and the list of nouns, you want the image and a much richer description of that image. From the second problem, it is clear that just visual grounding of nouns is insufficient for the recognition of objects. That is, just knowing what does a tennis ball look like and what does lemon look like really does not help you to classify this object as either a tennis ball or a lemon. What you actually need to do is learn relationships between nouns to constrain the recognition problem. So in the English language itself, parts of speech such as prepositions and comparative adjectives are used to represent relationship between nouns. The Wikipedia definition of preposition says that a preposition is a word that indicates spatial, temporal and logical relationship of an object to the rest of its sentence. Here is a list of 50 most common prepositions in the English language, and the ones in the bold are of particular interest to us because of the utility in image and video analysis. Now, comparative adjectives are the words which relate two or more objects based on color, size and movement. For example, the word larger indicates relationship between two objects based on size. Now, one of the interesting questions that we'll try to answer during this presentation is, can we visually ground both prepositions and comparative adjectives, and can we use these grounded models of prepositions and comparative adjectives to learn and represent relationship between objects and improve recognition itself? For example, if I have to label in this image I have to label sun in this image, it's a hard problem because both the real sun and the reflection of the sun look like sun based on appearances. However, if I can visually ground the word above such that B above A means y coordinate of B is more than y coordinate of A, and I know from the knowledge of my world that sun mostly occurs above C, by recognizing C in the image, I can very easily say that the above region should be the sun and not this region. One of the other interesting questions that I'll try to answer during this presentation is, can we use richer annotations including prepositions and comparative adjective to constrain the correspondence problem itself? That is, instead of just using the list of nouns as a training data set, what you want to use is a much richer description in the training data set. For example, in this case, car is on the road, officer is on the left of the car, and so on. And once you have a model of the word on, that is 2 is on 1 means something like this, and you know in this image car is on the road, you can constrain the correspondence problem based on this relationship. That is, the green region is the car and the pink region is the road is more likely hypothesis that the green region is the road and the pink region is the car. So in this work, I'll talk about why we can use these hand-defined models of relationships. I'm more interested in learning classifiers for both nouns and relationships, that is prepositions and comparative adjectives simultaneously. So in this case, my input will be a large image data set with a richer description of the data set in terms of list of nouns and relationship between those nouns, and I'll try to learn the visual grounding of nouns, the visual grounding of comparative adjectives, and the visual grounding of the word on, prepositions. I'll also try to learn the priors and possible relationships between pairs of nouns. This will lead to a better labeling performance. Again, for example, the two hypotheses that this region is the sky and this region is the water is equally likely to the hypothesis that the above region is the water and the below region is the sky, just based on appearances. However, if I can learn from my images and the language that in the world sky mostly occurs above water, I can very easily say that the left hypothesis becomes more likely. So before going into details of how I would learn the noun and relationship models, I would first talk about some representation issues. Each training image is first segmented into regions. Each region is represented by a feature vector based on appearance and shape. For example, we can use mean RGB values, mean intensity values, convexity, moments of inertia, and so on. Now, models of nouns are based on features of the region. However, relationship models are based on differential features. Differential features are the features which are extracted from a pair of region. For example, one of the differential feature could be difference in average intensity of the two region, or difference in location of the two region, and so on. Now we'll make a simplifying assumption. That is, each relationship model is based on a single differential feature for convex objects. For example, in this case, below is based on differences in y values, y coordinates. And once we have made this simplifying assumption, learning models of relationships would involve the feature selection. That is, what feature is this relationship word related to? Now, to solve the learning problem, I need the solution of the assignment problem. That is, I need to know what region is associated with the word car, what region is associated with the word road, to know what does a road look like, what does a car look like, and what does the word on mean. However, the assignment problem itself depends upon the solution of the learning problem. That is, I need to know what does a road look like, what does a car look like, and what does the word on mean to really associate regions with the words. So now we have a classical chicken and egg problem. In this case, we'll treat assignment as a missing data and formulate an EM approach. So in the E step, we would compute the noun assignments based on the previous iterations noun and relationship models. And in the M step, we would, for the noun assignments computed in the E step, we will recompute our new relationship and noun models. Like all EM approaches, our approach would need an initialization. We can use any of the image annotation and initialization, and in this case, we'll specifically use the translation-based model which appeared in ECCV 2002. So now when we did our experiments, we found most of the relationships were learned correctly. That is, above was associated with the differences in y values, below was associated with differences in y values, and so on. One of the interesting things is the word behind. Now to have a good representation or the good association for the word behind, you need a 3D model. Whereas in our case, the word behind was associated with a difference in texturedness. So you can see that this approach tries to see the association between the differential features and the relationships itself. Now some of the features, some of the words were associated with the wrong features. For example, in and on top of are hard to capture by color, shape, and location features. Now in case of taller, most of the tall objects are thin and our segmentation algorithm tends to fragment them, and therefore this was also associated with the wrong feature. Now during the inference, again we first segment the image into regions. Each region is represented by a noun node in the Bayesian graph. Between every pair of noun node, there is a relationship edge which draws its likelihood from the differential features extracted from the pair of regions. Therefore, our inference equation would consist of 3 terms. The first term indicates how well the appearance of noun matches the appearance of region. The second term indicates how well the appearance of relationship model matches the appearance of differential feature. And the third term is a prior term on relationships given the pair of nouns. So for experimental evaluation, we used Corel 5K dataset. We used 850 training images. Now the tags or the list of nouns are provided by the Corel dataset itself, and we manually labeled some of the relationship between these tags. Our vocabulary consists of 173 nouns and 19 relationships. We use the same segmentation and feature vector as used in the ECCV 2002 approach of Duiglu et al. Our quantitative evaluation of training is based on 150 randomly chosen training images out of these 850 images, and our quantitative evaluation of testing is based on 100 test images. Now we would first like to evaluate the performance of our approach on training itself. That is, how nicely our approach is able to associate regions to words in the training. So here are some of the examples. Now the left column shows the performance of Duiglu et al., that is the ECCV 2002 approach, and the right column shows the performance of our approach. Now as you can see, some of the words are associated with the wrong regions in the case of Duiglu et al. For example, the reflection of the sun is labeled as sun, this region is labeled as sea, and so on. However, if you apply extra constraints from this language, like richer descriptions, like sun should occur above sea, and so on, you obtain a much better assignment. Here is another example where statue is associated with the wrong region. However, once you apply a constraint that statue is above rocks, you obtain a much better assignment. Now one of the things to observe is that this relationship is image specific. It is not necessary that this relationship should hold throughout all the training images. So therefore, we have two kinds of relationships. The ones which are kind of ground truth or are true throughout the data set, and the ones which are true, which are image specific or the local relationships. Now quantitatively, we compare the performance of our approach based on 2 measures. The first measure counts the percentage of each word correctly labeled by the algorithm. the second measure counts the number of regions correctly labeled by the algorithm. To understand the difference between the two measures, let me give you an example. Suppose we have two algorithms, and the algorithm 1 can label sky correctly and the algorithm 2 can label car correctly. Now based on the first measure, both the algorithms have similar performance because both the algorithms can label one word each. However, based on second measure, the first algorithm has a better performance because the first algorithm will be able to label more regions correctly since sky occurs more frequently than car. Now we quantitatively compare the performance of our approach with IBM Model 1 and Duglu et al. Now IBM Model 1 is another translation based approach or co-occurrence based approach. Now the left green bar shows the performance of IBM Model 1, the right green bar shows the performance of Duglu et al. Now the left red bar shows the performance of our approach when initialized by IBM Model 1, when the EM is initialized by IBM Model 1, and the right red bar shows the performance of our approach when EM is initialized by Duglu et al. Now as you can see, based on both the measures, our approach outperforms both IBM Model 1 and Duglu et al., and in some cases the percentage improvement is as much as 35%. Now one of the interesting things to observe is this magenta line. This magenta line indicates the performance of our approach when the relationships are not learned but are specified by the humans. That is, a human specified that above means differences in y values or left means differences in x values and so on.
So what is semantic range?
So the semantic range is actually counting how you can label uncommon words. So basically an uncommon word and a common word is treated equally in the semantic range. Whereas in this case a common word is given more weightage than an uncommon word. So so basically this shows that our approach can label both uncommon words nicely and the common words nicely. So one of the problems with co-occurrence based approach has been that they usually do very good on common words, not on uncommon words. And that is why this measure actually counts how our approach performs on uncommon words as well.
Okay, but as far as I understand, there is a little trick here because at least Duglu et al. Is not using all of the data that's available to you, right?
Yes.
Because you are using extra annotation that they are not using.
So what this is showing is that what is the importance of using prepositions and comparative adjectives. It is just showing that. I'm not saying that we are better than Duglu et al. And something like that. What I'm saying is that this shows that we should use prepositions when we are using language itself. So we should use rich language instead of just using nouns and verbs.
So how did you get those prepositions?
So
they're not in the Corel data set.
Yes, so that's what I said. In the training in the data set, we manually marked ourselves the relationships in 850 images.
I see. That's what I see.
Sorry. Okay.
The other issue is, so you have two kinds of relationships, right? One is that sort of ground truth,
Right.
valid for anything, and then there is image specific.
Right.
So how did you learn?
So in this case, there is no feedback. That is, so in this approach, so the next approach will have the feedback. That is, it will try to find out what is a ground truth in the world and try to learn a semantic model of the world based on the ground truth data set. And then try to apply that thing in the training of other images as well, where the ground thing is missing. But in this case, it's just doing image specific. There's no transfer of labels from one image to the other. But you can do that as I'll show in the case of Beyond Words. Okay, so here is the labeling of test images, that is when a new image comes. Again, the independent labeling of Duglu et al. Leads to bad labels. For example, this region is labeled as water. However, when you apply the simple constraint that water should not occur above clouds and so on, you obtain a much better assignment. Again, reflection of sky is labeled as sky. However, applying simple constraint that sky should occur above water and so on, you obtain much better assignment. Yeah.
So on these results that you're showing, a bunch of the segments don't have any labels. Does that mean that they're unlabeled?
So basically, okay, can I answer this after the next slide?
Okay.
That will actually help me to answer, how we chose the detection threshold. Okay, so to quantitatively compare, we compare the set of annotations provided by our algorithm to the set of annotations provided by the ground truth from the Corel dataset. Now we chose the detection thresholds such that the number of missed labels by our approach and Duglu et al. Is almost similar. And at this detection threshold, we compare the number of wrong labels produced by each algorithm. So basically what we are trying to do is we are trying to set a detection threshold based on the number of missed labels should be almost equal. So in case of Duglu et al., to generate 100 mislabels, you have to do much more labeling. And that is why some of the labels are very stupid, as you can see in this case. So you basically keep a detection threshold very low in this case, so that you can you only miss around 200 words in this case. Now, as you can see, the previous experiments, the results of the previous experiments are confounded by the bad segmentations. That is, you do not know, is it because of the bad segmentations my approach works better, or is it just because of the some kind of association. So what we did was, we did another small experiment. In this case, we took 75 training images from MSRC and Berkeley datasets, and in this case, the segmentations are perfect and given by the humans. And we used the vocabulary of 8 nouns and 19 relationships in this case to learn. Again, in this case where we are using perfect segmentations, we see a similar percentage improvement over Duglu et al. So basically now you can say that even in case of perfect segmentations, or you have better segmentations, you still need prepositions to do better. Okay, so before I go to the second part of videos, let me first give you just 1 minute review of what I talked in the first about. So traditionally, the link between language and computer vision has been in terms of just nouns and verbs. What we are trying to do in this case is, we are trying to link other parts of speech like prepositions and comparative adjectives to semantic context or the concept. So basically, more specifically, what we are doing is, we are using rich descriptions of images to do better learning of appearance models, and we are using grounded models of prepositions and comparative adjectives to provide us contextual model for labeling of new images. Now once this approach performed so well, we thought we have to try this on videos as well. Maybe this works equally good and much better in videos. So what we did was, in this case, we'll have, instead of having spatial segments, we have spatio-temporal segments of human tracks. Instead of having nouns as annotations, we have verbs as annotations. And instead of having just spatial prepositions, we have both spatial and temporal prepositions. So here's a spatial preposition and here's a temporal preposition. Now as an output, in this case, we would obtain the visual grounding of verbs and the visual grounding of both spatial and temporal prepositions. For experimental evaluation, we used 40 baseball videos from 2007 World Series. Our action vocabulary consists of pitching, hitting, swing, miss, run, catch, and throw. Our relationship vocabulary consists of just 13 prepositions, out of which 9 are temporal and 4 are spatial. So as you can see, again, our approach outperforms the co-occurrence-based approach by a huge margin. However, still the performance of our approach falls short of expectations, because if you see, at a 45% precision, we just have 37% recall. So the question is, why doesn't beyond verbs work in the case of videos? Or what goes wrong in the case of videos? So what I'll do is, now I'll take a step back and see what problem are we trying to solve in the case of videos, and then come back and try to answer why does not beyond verbs work in the case of videos. So videos involving human activities are structured. That is, every video has a story associated with it. For example, the story of the first video is, pitcher pitches the ball, the batsman hits it, he then runs towards the base, first base, whereas the fielder runs to catch the ball and he catches the ball. The story in case of second video is much shorter and much simpler. That is, pitcher pitches the ball and the batsman just misses it. So if you notice, these storylines can be used to provide contextual information for recognition of activities. For example, if I know that a spatio-temporal segment is associated with the hitting of the ball, it is highly likely that the spatio-temporal segment just preceding it should be the pitching of the ball. However, the contextual information hidden in these storylines is not pairwise but of higher order. For example, by just knowing that a video contains the running of the fielder, I also know that the same video contains the pitching of the ball, the hitting of the ball, the running of the batsman, and the catching of the fielder. And all these activities occur in a very specific order. So one of our goal is to represent this higher order contextual information hidden in these storylines. However, as you can also observe, storylines vary across videos in a domain. That is, there can be substantial variation in terms of agents, actions, and the relationship between actions themselves. So what we need is a model that can compactly encode the storyline variation and represent the contextual information hidden in these storylines. So this model should be able to encode the space of allowed storylines for the domain. So in the case of beyond verbs, what we did was we projected these higher order constraints onto pairwise constraints. And as expectedly, projection of higher order constraints onto pairwise constraints would lead to loss of information. For example, if I try to project this part of a storyline where a fielder runs towards the ball, he catches the ball and he then runs towards the base. If I try to project this part of a storyline onto pairwise constraints represented by prepositions, I have the following two constraints. That is, the fielder runs before catching and the fielder runs after catching. As you can see, both these constraints are contradictory to each other and hence the loss of information. One of the other reasons that why beyond verbs doesn't work in a case of videos is when you project these storylines onto pairwise constraints, your problem becomes under constraint. Let us for example consider this stop sign scenario with two cars. Now in this case there are four possible storylines. That is, the car A1 stops, then car A2 stops, then car A1 continues, finally car A2 continues. In the second case, car A2 stops first, then car A1 stops, then car A2 continues, and finally the car A1 continues. In third case, there is only one car, that is car A1 stops and it continues. And finally, in the fourth case, there is only one car A2 which stops and continues. Now if you try to project these four storylines onto pairwise constraints represented by prepositions, you have the following four constraints. However, these constraints are insufficient to restrict the space of storylines to just four of these, and it allows some weird storylines like car A2 stops, then car A2 continues, and out of nowhere a car A1 appears on the stop sign and it continues. So what we want is a model which can restrict the space of storylines to the ones we have seen till now. So in this part of the talk, I'll present a storyline model which is a contextual model for action recognition, and it encodes higher order constraints. It also encodes substantial variations in storylines in terms of agents, actions, and relationship between actions. Ideally, we would like the links in the storyline model to be based on the causal dependency. That is, one action being prerequisite of another. For example, I would like pitching and the hitting to be linked by an edge because pitching is a prerequisite of hitting. That is, for someone to hit a ball, someone should have pitched the ball. Furthermore, the parameters of the hit, that is the time of hit, physically depend on the parameters of the pitch, the time of pitch, and the velocity of pitch. I'll also present an approach that can simultaneously learn the storyline model and the visual counting of verbs from richly annotated data. And finally, I'll present an approach to simultaneously estimate the storylines and recognize individual actions, and I'll also show that simultaneous estimation of storylines and individual actions would lead to better performance. So before I go into the details of how we learn a storyline model, let me first talk about the storyline model representation. We use a modified AND-OR graph to represent the storylines. Now, AND-OR graphs were introduced by Zhu and Mumford to represent grammar of images. However, in our case, we are using it to represent the causal graph structure. Now, AND-OR graph consists of two kinds of nodes, AND nodes and OR nodes. OR nodes define possible alternative configurations or different possible storylines from a point in time. For example, this pitching node is an OR node because after pitching, batsman can either miss the ball or he can hit the ball. Similarly, catching is an OR node because after catching, the fielder can either throw the ball or he can himself run towards the base. Now, AND nodes are the nodes which represent bifurcation in the graph. That is, one activity followed by two or more activities. For example, hitting is an AND node because after hitting, the batsman runs towards the base and the fielder runs to catch the ball. Now, as you can see, storyline instantiation in this case would involve making selections at the OR node. That is, to get a storyline, you need to make decisions at the OR node. For example, at pitching, you need to make a decision whether you see the missing of the ball or the hitting of the ball. If you see the hitting of the ball, then you need to decide at catching whether you see the throwing of the ball or the running of the fielder. Now, our goal is to learn the storyline model from richly annotated data. Now, learning a storyline model would involve learning the structure of the storyline model, learning appearance of each action, that is each node, and learning the conditional distributions between nodes linked by an edge. For example, if hit and pitch are linked by an edge, I would like to learn the distribution of time of hit given the time of pitch. Like previous problem, this is also a chicken egg problem. The track labelings depend on the structure and the parameters of the storyline model, and the structure and the parameters of the storyline model themselves depend upon the track labelings. So again, we use an iterative approach. Let us assume we have some initial storyline structure to begin with. Using this storyline structure, we label each track in the training videos. Now, as you can see, some of the labelings might be wrong. For example, this track, blue track, has been labeled as run, whereas this is catch. And similarly, this purple track has been labeled as throw. Now, one of the reasons for bad labelings is the bad appearance model to initialize with. One of the other reasons for bad labeling is the bad initial storyline structure. For example, in this case, it does not allow running of the fielder after the catching of the ball, and therefore this track has to be labeled as throw. Now, based on the track labelings obtained in this step, you relearn your appearance models and the conditional distributions conditional distributions of the edges. Based on the new appearance model and the new conditional distributions, you redo the track labeling, and some of the track labelings might improve. For example, due to a better appearance model of catch, you have a better labeling in this case. Now, as you can see, during these iterations, the structure of the storyline model remains fixed. We are just iterating between the track labelings and the parameter estimation. Once the parameters have converged, you locally modify your storyline structure and create your storyline proposals. Out of this storyline proposals, you select the best storyline proposal based on some criteria. I'll talk about this criteria in the coming slide. Now, based on the new storyline model and previous iterations, appearance and conditional distributions, you redo the track labelings. Again, some of the track labelings might improve due to better storyline structure. For example, since now your new storyline structure has the running of the fielder after catching of the ball, you obtain a correct label for the purple track. Now I'll talk about the criteria for the storyline proposal selection or the structure selection. Now, this criteria consists of 3 terms. The first term indicates that we prefer simple linear structures over complex structures. The second term indicates we prefer smooth conditional distributions that avoid overfitting. And finally, we prefer a storyline which can explain not only our videos but the captions associated with these videos. So basically, you can see in this case we are trying to learn semantic models from both the language and the video itself. Now, for initializing our iterative approach, we need 3 things. We need to find the human tracks in the video, we need to initialize the visual grounding of the verbs, and we need to initialize the initial storyline structure. For initializing the visual grounding of the verbs, we'll use the results of beyond verbs approach that I talked about in the previous slides. For initializing the storyline structure, I'll use a greedy approach. So in this case, we initialize our AND OR graph with the minimum number of nodes required to represent each action in the caption. For example, in this case, I need 2 nodes for run, 1 node each for hit, catch and throw. Once you have populated your initial AND OR graph, you need to predict your links. Now, for link prediction, we use time as a cue to infer causality. That is, if A immediately precedes B, then A is a parent and B is the child. So, using the captions and Allen's interval logic, we first obtain a timeline for each video and obtain the weight of each possible edge in the graph. And then we use a greedy approach where edges are added based on weights such that no loops are introduced. Now, when a new video comes, you need to infer its storyline and you need to recognize individual actions in the video. Now, again, the storyline inference would involve making selections at the OR node. For example, in this case, I need to make selections at pitching node and the hitting node, and therefore there are 3 possible storylines: pitching followed by missing, pitching followed by hitting followed by catching, and pitching followed by hitting followed by running. Not only do you need to infer the storylines, but you also need to establish the mapping between the nodes in the storyline and the tracks in the video. So this mapping can be 1-to-1 for example, one track assigned to one node, many to one, that is many tracks assigned to one node, and one to many, that is one track assigned to many nodes. Now we want to simultaneously estimate our storyline and mapping such that it minimizes a cost function based on three terms. The first term indicates we prefer storylines that explains most of the tracks in the videos. For example, the left storyline is a bad storyline because it only explains two tracks, that is the peach track and the yellow track, whereas the right storyline explains all the three tracks. Not only do we need our approach to explain all the tracks, but we also need the appearance of each node to match the appearance of the track. For example, in this case, the left storyline is a bad storyline because the appearance of catch node does not match the appearance of each track. And finally, we prefer a storyline and mapping that satisfies the spatiotemporal constraints. For example, the left mapping is a bad mapping because in this case, hitting does not occur before running. For experimental evaluation, we use the same 40 videos we used in the case of Beyond Verbs. For initializing the human tracks, we used an HOG detector to detect humans and then cluster these detections to extract human tracks. Now this kind of an approach results in fragmentation of true tracks, that is, each track is not directly associated with one action, and similarly some tracks would also contain transition from one action to another. Now each track is described by a bag of word representation of spatiotemporal interest points. Our quantitative evaluation of training is based on 40 training videos, and our quantitative evaluation of test is based on 42 test videos. Now again, we would first like to evaluate the performance of our approach on the training dataset itself. That is, how nicely our approach can assign tracks to action labels. The y-axis shows percentage correct assignments of tracks to action labels. The green line shows the performance of co-occurrence based approach, that is 33.6. This is not up to scale. The red line shows the performance of Beyond Verbs approach, and the blue line shows the performance of storyline model. Now as you can see, in this case, there are three blocks. Each block represents inner iterations, that is, the structure remaining fixed, you only iterate between track labelings and parameter estimation. Between each block, we take a structure step, that is, we modify the structure. Now as you can see, the performance of our approach improves with each iteration. This is either due to better parameters or a better storyline model, for example in this case. Now one of the interesting things to observe is sometimes the performance of our approach falls when you do take a structure step. This is because when a new edge gets added, you do not have correct parameters to initialize with. And once your parameter estimation continues, the performance improves. Now when a new unseen video comes, you need to infer its storyline and the assignment of tracks to the nodes in the storyline. Now the left graph shows the storyline inferred for the video, that is, in this case, the pitcher pitches the ball, the batsman hits it, he then runs towards the base, whereas the fielder runs to catch the ball, he then throws the ball towards the base, and the fielder at the base catches the ball. Now the mapping between the nodes in the storyline and the tracks is shown in color. For example, pitching is mapped to the blue track, hitting is mapped to the cyan track, and so on. Now not only can our approach infer the storyline and recognize individual actions, it can also generate a good textual description of the video, because this model is itself learned from the language itself. The currently active part of the text is shown in red, that is, at this frame what part of the text is active. Now here is another example where the storyline inferred is much smaller and much simpler. Again, the mapping is shown in color. Now one of the interesting things to observe is that even though in this case the fielder runs towards the ball, but since our video image processing part or the video processing part does not generate a track for the running of the fielder, there is no node for the running in this storyline. And once it zooms in, it has a good track for the it starts a track, and therefore you have, and at this point it's just the catching left, and therefore it just infers catching. Here are another example, some more examples. Now, one of the things to observe is in these cases, we are only showing the tracks which have been associated to a node. However, the number of tracks generated by the video processing part or the image processing part is much higher. We are only showing the ones which are being linked to some node in the storyline. Now here you can see there is a transition from the same red track contains the catching and the running of the fielder, but because there is another track for the running, it prefers that track for running. Now quantitatively, we compare the performance of our approach to beyond verbs and IBM Model 1. At a much higher precision of 80%, we have a much higher recall of 85%. Okay, so I'll not get time to talk about my other work, but I'll just give you a brief 1-minute summary of my other works, which is related to this line of work. So in the first part of the talk, I talked about noun-noun relationships based on prepositions. In the second part of the talk, I talked about verb-verb relationships based on causality. However, I have also looked into noun-verb relationships. More specifically, I have looked into a contextual model which combines human motion analysis, object recognition, and object reaction recognition. Now, object reaction is the effect of an action on the object. For example, if you press a button of a flashlight, there is an illumination change. The constraints are based on spatial compatibility between action and object, functional compatibility between action and object, and temporal orderness. Our results indicate that the performance of object recognition improves drastically when you add human motion cues to the object recognition. Similarly, performance of action recognition improves drastically when you add object cues to the motion analysis. Then I later extended this approach, and in this case, we are trying to recognize actions from static images. So in this case, you do not need any motion information to recognize actions. You just recognize actions based on relationship of a human with the rest of the objects in the environment. I have also looked into how we can use other visual cues to constrain the learning problem. More specifically, I have looked into how we can use a single shape sketch of a car to learn an appearance model of the car and the appearance model of its context. So now we can learn an appearance model of the car and its context from training images like these, where the object of interest is so small and you do not need any bounding box in the training dataset. Here are some of the test results on the test images.
Wait, so what is going on here?
Probably I should talk about it because basically what you're trying to do is so basically your problem again is the co-occurrences. You have to label each of the shift or surf feature as either belonging to context or the object. So basically if you try to do just based on co-occurrences, so basically the goal of this project was to evaluate, do you really need rich language, or can you just do it with other visual cues? So what we are trying to do is, we are trying to obtain the labels just based on co-occurrences, and that is how you obtain the labels. Very bad, because the object of interest is so small, co-occurrences do not work in such small cases and such cluttered scenarios. However, if you add a single shape sketch in the Django style, and you try to now learn your appearance model by constraining the problem such that so basically now that your problem has 3 constraints. The first, it should satisfy the co-occurrences of the features. There should be intervening contours between the foreground features and the background features. There should be strong intervening contours, and the shape of the intervening contours should be matching to the shape of the sketch provided by the human. And so basically so when you do this, and then you can learn a good model. So basically now this is the kind of labeling you obtain in the training if you constrain the problem with these 2 extra constraints. And you can have a much better labeling, and therefore a much better model you can learn, and you have very good results in the test. Okay, to conclude, I have shown that language can provide top-down information or contextual information which is important for reliable learning of visual models. More specifically, I have shown that prepositions and comparative adjectives can provide relationship constraints that our learned models should satisfy. I have also shown that how language can provide a way to represent context and learn context from very rare or fewer instances. As part of future work, we would like to see how we can further constrain the problem using adjectives and adverbs, or how you can have a much richer contextual model or semantic model based on adjectives and adverbs. We would also like to use the hierarchy in the language or the ontology in the language to maybe have a better segmentation itself. And finally, we would like to attain our goal where we can use the written description of an object to help learn the visual models of the object. During the second part of the presentation, I have shown that visual inference involves not only object and action recognition, but inferring the plot of the whole video. Now this plot, in our case, represents higher order contextual information. So as a future work, what I would like to do is have a much richer representation of the storyline models. So for example, if I show you this image and I ask you, what do you see in this image, or what is the joke hidden behind the image, your answer might be a lot different from a computer vision answer. So the computer vision approaches can tell you they see 2 fishing rods, 2 persons, water, ledge, cliff, and so on. And this is a very ideal vision algorithm. Maybe our beyond nouns approach can also tell some kind of relationship between these objects. However, what you and we see is that the person 1 is trying to steal the fish caught by person 2. So what we would like as a future part of future work is to represent intentions in the storyline model itself. That is, your storyline model should represent the intentions of the actor, and these intentions can be learned based on causal relationships between actions and based on contextual relationship of the actor with the rest of its environment. And finally, going back to our original goal of making intelligent machines which can interact with humans, we would not only need visual grounding of nouns and verbs, but we'll also need visual grounding of other parts of speech like prepositions and comparative adjectives for a much effective man-machine communication. And we believe our work is a step in that direction. So these are the people with whom I have worked. Of course, you know Jambo and Larry. And these are the publications on which this talk was based. I didn't talk about these last 3, but I a little bit talked about all the ones in the book.
Questions?
Yeah.
Baseball is a very structured activity, much more so than just our everyday life. How do you plan to deal with that?
So, I mean, our approach is actually very good only for structured. And somehow, I can say by luck, humans have tried to impose structures on everything. For example, it's a traffic light scenario. There's a lot of structure, like I showed in the example. In case of airports, there's a structure. I mean, you just go, you check in. So, I mean, because humans have designed their world structurally, this approach is applicable to lots of cases. However, it's not applicable to dramas, like, I mean, as you can understand. And yeah, so it's basically applicable. So yeah, I mean, that's a good critique that it's only applicable in the structured case. But kind of my defense is that most of the scenes are structured, most of the videos are structured in the world.
At the static image case, I came a little late,
Yeah.
so sorry to ask you.
Yeah.
What is given to the learning program is segmentation and the sentences.
Yes. So segmentation.
No assignment of
Nothing.
labels
No.
to any region.
Not even the appearance models of these prepositions. It doesn't know what does this preposition mean. All it knows is that this. So I'll show you what it actually has. Yeah. Yeah, this is the input. So there is a lot of, I mean, I have shown only 3 images, but there are a lot of images and some description of these images, like bear is near water in this case, field is beside water in this case, field is behind bear in this case, bear is in water. And in this case, you do not know what does near mean, what does bear mean, and you do not have any assignments of nouns to the regions in the image. You have to solve all these things simultaneously.
And then in using these inputs, those language inputs,
Right.
in the learning program,
Right.
you used a specific segmentation program?
Yes. So this is kind of, I will say, a restriction I'm in. So ideally what we would like is a multiple segmentation kind of an approach where it selects from multiple level segmentations. So the problem with this is right now the segmentations are really bad. So we are using the segmentation algorithm as used by David Forsyth and other people in their ECCB 2002 so that the comparison is fair. So these are the kind of segmentations. As you can see, there's no reason it should have this kind of a line or something like that. So I mean the segmentations
that is the kind of segmentation that you use
yes,
for learning and also at
for the
time
testing.
of testing.
Exactly.
Okay.
And that is why
you also showed if the segmentation is
perfect, then also there is equal improvement.
Now, if the segmentation is perfect for both learning stage and recognition stage,
Right.
what was the overall result? I
So,
forgot the number.
yeah, sorry. It's the same improvement. If you see, it's almost the same improvement, and the improvement on the magenta line is almost similar as well. It's exactly similar.
Not comparing with other people. In your case,
Yeah, so this is my result, 75% correct
What
assignments.
was it before?
In the before, so this is on the imperfect segmentations. I didn't, maybe
so
I'm
at the
getting,
time of learning,
right,
the labeling of the regions.
Right.
Imagine that I gave you perfect segmentation.
definitely, yeah.
At the time of learning, as a result of the learning, how much labeling, what percentage of labelings were correct?
So this is what I mean, if the segmentations are perfect, which in this case 75 training images, and my vocabulary is 8 nouns and 19 relationships, the other approach gave just 50% correct assignments, whereas my approach gave 70% correct assignments at the time of training, when the segmentations are perfect.
At the time of learning?
At the time of learning. I didn't do at the test, because our assumption is that if you have a better assignment at the training, you learn a better model, and that is why you'll probably do better in the testing as well. Because, I mean, one of the reasons we didn't do on testing is due to the lack of, images with correct, perfect segmentations. So there we.
For that one, I'd like to know a little more analysis of errors of labeling. For example, imagine that extreme case that if the particular label appeared only once in the whole learning set, then, well, in general, well, who knows, it may be actually still do it. But
so
the point is that, I mean, depending on the situations, so if you analyze the results of the learning for the learning set with a perfect data segmentation, then you should be able to evaluate how much, well, what can be indeed learned. Is that bar,
yeah.
What does bar mean?
This bar shows the performance of the percentage correct assignments when relationships are specified by the humans. That is, human said, this is the relationship model for above, this is the relationship model for below, and so on. So, I mean, you can see at perfect segmentations, I mean, if the relationship models are not learned but are specified by the humans, you have 80% correct, 80% correct assignment. And the reason it's just is restricted to 80% even in the case of perfect segmentation is that our feature set is actually not very good as well. But we use the same feature set which the other approaches have used. So I mean, and the question that how would analysis of how uncommon words would do in case of perfect segmentations, we didn't do that analysis because we only used common words. We wanted, because it's such a small training data set, we cannot really understand the effect of uncommon words in such a small training data set. I mean, probably you need hundreds of images if you have to understand the effect of uncommon words.
Well, is it more than that? For example, just imagine that there are pictures
Right.
given in the learning set,
Right,
which is made of 2 regions.
right,
And it says, sky is above water.
right,
Then without looking at any other image at all, it should be sky is the upper region
Right.
and water should be lower
Right.
region.
right. I mean, definitely, and that is why. But given that you have such bad features you are still getting 80% correct. The problem with perfect segmentations also is you'll never have good features of good model of in, because we are not doing any 3D analysis. We don't have good model of behind, and all these words are really important to do a good analysis, perfect analysis. I mean, as you said that just by using the word above, if there are two regions, that's what we actually saw in the case. I mean, in images like these, where is it? Yeah, in images like these, it would work perfect. I mean, if you have a very good model of in. So, I mean, the problem is, even in these images, you need a very good model of in water or on top of field, and you don't have good models of these because you are not doing any 3D analysis with these images. And that is why, so these are two reasons I would say. There's no 3D analysis, and there is no good feature vector for these regions.
Oh, I see. So you're even learning above,
Yes.
of above.
Yes, exactly. And that is why, if you see, it's basically trying to understand. So basically so as you can also say, how many prepositions are there? I showed just 50 prepositions. Maybe I should just specify by hand. But since we, at some point of time, we want to use comparative adjectives, which are, I don't know, which has a very huge vocabulary of comparative adjectives like larger, brighter, more green, more red. Similarly, you want to use adjectives at some point of time in future. So basically, you should have an approach where you can learn these words also from the data sets. Your data sets can not only allow to learn nouns and verbs, it can also allow us to learn prepositions and comparative adjectives. And as part of future work, we like to see that can they also allow us to learn adjectives itself. And once we can learn all these models from the data itself, then we can use huge text analysis to learn our semantic concepts. That is what we are trying to do in the second part. That once you can learn these things, you can learn a good semantic model of the videos.
Now, in that learning, sorry, Sebastian.
No,
in that learning of meaning of above, for example, what primitives do you give?
So
Nothing?
So this is the, we give nothing. We are just trying to associate above, the occurrences of above with the occurrences of differential features. So that is, just 1 second. Okay. So, sorry. Since you are only trying to get associations between the relationship words and the differential features, what we are trying to do, so for example, above was done with differences in y values, below was done in differences in y values, left differences in x values, right differences in x values, and similarly.
Oh, I see. So correctly means that if left is learned, if associated by this result,
Exactly.
learning,
Exactly.
by the difference of x,
Right.
smaller and larger,
Right.
then you call it correct.
Correct. So, one of the interesting questions is, can you say I learned behind without doing any 3D analysis? So what we got for behind is difference in texturedness. That is, front regions are more textured, behind regions are less textured. So I don't know if this is the correct definition of behind, but given these circumstances, kind of analysis we are doing, probably this is the best feature association for behind. And that is why we get these.
So I missed most of the talk
Yeah.
that I told you I would.
Yeah.
Let me talk to you. But so on choosing those features, it's a little strange, right? Because to be the devil's advocate, right? One could imagine a situation where you're going to try your system and you're going to add features. In fact, you're going to add features that you know. I mean, if you take the difference in X or the difference in Y, well, that's, those sounds like the right features to use
Right.
for those words, right? So how do you guard against that? In other words, how do you guard against somebody knowing what word you're looking for in the first place, and therefore defining the features that one knows will help?
So, what we did was we only used the differential features of which the real features are given. So basically, if the feature of a region is intensity, RGB values, and so on, we did all the differencing. Difference in R value of two regions, difference in G value of two regions. So we are only using that.
And the features of the regions are the standard features.
Standard features which everyone is using, which is
there's no balance.
Right. And just to say, number of features, differential features, are probably much higher than the number of relationships. So the problem is not just one-to-one association. You have to select out of all these also. So the number of features will be.
Yeah, well, that's true of relationship, but that's good. How is that going to work for adjectives then?
So I mean, so in the case, it's hard to say because I have not worked on adjectives, but I mean, what other people have done in case of adjectives is they have treated adjectives as nouns. And they said that, okay, if it's a noun, then it's just the same problem. Red, in the case of red, the adjective should learn is high red values in the Gaussian and does nothing else. So, I mean, in my case, what I think is, I mean, I'm just interpolating. I have no experience with this, I mean, but I have thought about it a little bit, so that's why I'm interpolating. So, in adjectives are defined, so basically you use adjectives when the properties of the mean object is different from the property of the specific object you're talking about. And that is where you can use, again, the differential features. You difference from the mean of the object. For example, you only say red apple when it's different from the real apple, I mean, much redder from the other things. So that, but again, it's all speculative. I don't know if I should even talk about it without even working on it.
From the historical perspective, your work is very interesting and indicative.
Right.
Because if we look back 70s and 80s, as an old time.
Right. No, actually, Marshall and we talked about the same thing.
Don't break it.
Okay, yeah.
We try to do all these kind of things by hand coding above, behind, below, left, right, besides, bluer, and so forth.
Right.
In, on top of, and so forth. And then, frankly, the result was not as good as we thought it would. And then, now of course we have to realize that at that time we didn't have EM,
Yes.
we didn't have learning methods, we didn't have enough powerful computer to search for big combinatorics,
Right.
but yet it was not successful. Therefore people said, well, maybe the idea was wrong, like above. And then indeed I wrote the paper at that time and said, well, if we think of it, using the word like above, on is wrong because those are scene words, not picture words, like on especially. On the road. In the picture can have a lot of different situations. In the picture it could be above, could be inside of, could be even left of, and so forth. And then based on these discussions, we went on to some much lower level research saying that, well, from image, we should be able to figure out some of those more scene relationship from texture gradient and this and that. Now, you're saying, effectively, it's okay to go back to those time and then do it again with these new tools. Is that what you're saying?
Yes, I'm saying that since our statistical power, our data sets, and our statistical power has increased drastically, I think we can go back and we can do the things the same way. We can use language the way you probably wanted to use in 70s. Yeah.
Statement.
Yeah. I mean, probably like, okay, one of the reasons I didn't do on the perfect segmentations, uncommon words is, because if you do uncommon words on perfect segmentations, you'll not notice anything. And that is the problem I guess you might have also seen in your case. It's the power of the huge data sets which is actually helping you in doing.
Well, segmentation is really a part of this.
Right.
Because unless the segmentation is correct, meaning of above, behind, below, left, right, is not correctly assessed.
Exactly.
So, as you said, it's a chicken and egg problem. Right.
Right, exactly.
All right, well, let's thank the speaker. Endurance test. He is going to be here also tomorrow until afternoon or so?
Anytime. If there are a lot of other people who want to meet me, I'm happy to meet them.